We're now going to discuss the chemical properties and chemical reactivities of triacylglycerols. We're going to talk about 3 different chemical processes here, in addition to the esterification that we discussed in the previous section. Hydrogenation and hydrolysis are the first 2 that we're going to discuss. Remember, if you can't remember the exact processes, try to break down the word. Hydrogenation, if you take the first half of that word, is hydrogen. We're adding hydrogen to the double bond. Hydrolysis, the first part of that word is hydro, meaning water. We're splitting apart an ester by adding water to it. Hydrogenation of oils is what manufacturers do to make things like margarine or shortening. They take a vegetable oil that has cis double bonds, as we saw in the previous sections, and add hydrogen across the double bond. This converts the double bond into single bonds. By doing that, you're changing something from a liquid to a solid. And that's why it's going from a liquid version of olive oil over to a solid version of margarine. But if you think about margarine and Crisco and things along those lines, they're still pliable. You can spread the margarine. That's because they stop it before it goes to 100% completion. If they did it to 100% completion, it would be extremely hard and brittle. So just to give you an example, here originally was a double bond. There were 1 times plus 7 more is 8, 9, 10, plus 7 more, 17, 18. 18 carbons originally. 1 plus 16 is 17. 1 more is 18. They both have 18 carbons in them. This started off as a double bond. It's now a single bond. That's the result of the hydrogen being added to the double bond. Now, originally, they were cis, meaning that they were coming off the same side. They're both going down in this example. Unfortunately, when we do hydrogenation, a lot of the double bonds do transfer over to saturated, but not all of them. Some of them form this trans double bond, meaning one's going down and one's going up. They're going in opposite directions, which is making it trans. And you will see this on packages in the grocery store. It'll say contains trans fats or contains trans oils. What they're referring to is this bond right here. If we look at the shape, it's a zigzag shape, just like a saturated hydrocarbon. So our bodies read it as a saturated fat. However, it doesn't react 100% like saturated fat. It actually contains more energy than a regular double bond, than all single bonds. And that's creating a big effect. So, most naturally occurring fatty acids are cis double bonds. During hydrogenation, the cis double sometimes, not all the time, contains trans double bonds. In a body, it acts like saturated fatty acids because of the shape. Because they look exactly like a saturated hydrocarbon. And we are getting a decent amount of calories from these trans fats. Unfortunately, these trans fats have a tendency to raise LDL. That means low density cholesterol. low-density lipocholesterol. That's the bad cholesterol. That's stuff that clogs your arteries. HDL, which is the high density, is the good cholesterol, and unfortunately, it lowers that. So to give you a visual, here's your double bond originally. Through hydrogenation, we're adding hydrogen to the double bond, and we're breaking that double bond. Most of the time, it turns into a completely saturated fatty acid, which is what we really want. However, sometimes you're getting that trans where one goes up and one goes down. Another example of a fatty acid in manufacturing is Olestra. This is extremely popular in the late 90s. It was actually formed in the late 70s, early 80s as a way to give preemies a large amount of fat in a very small volume. Unfortunately, what they realized is that this is much, much bigger than a triacylglycerol. If you compare the size of this one to this, you'll notice how much bulkier the Olestra is. If you look closely, you're going to see a compound that looks extremely familiar from the previous chapter. It's actually sucrose. Here's the hexagon, here's the pentagon. And these were originally OH groups from the sugar. And that would be the carboxylic acid, or the alcohol portion of the carboxylic acid. They tacked on fatty acids, thinking that it would then create a really bulky fatty thing that would bind and make you gain weight really fast. Well, then they realized that none of it got digested. And so then they decided to start marketing it as an alternative to frying foods. However, it had a bad effect as far as digestion goes. People were having stomach cramps and things along those lines. So let's take a look at what we've learned with fatty acids. There are more unsaturated fats in vegetable oils. That is true. Vegetable oils have higher melting points than fats. While vegetable oils are actually liquid at room temperature, while fats are solids at room temperature. That means that fats take more heat to melt, which means this is false. It's the other way around. Hydrogenation of oils converts cis double bonds to trans double bonds. This is sometimes true. And animal fats have more saturated fats. This is true as well. The next chemical reaction we're going to discuss is hydrolysis. Remember with the triacylglycerols, we had originally OH groups bonded with carboxylic acid. So here's the OH group originally. This was originally from the carboxylic acid. With hydrolysis, you're going to draw a line between the O's. So here's one O, here's the other O. Draw a line between it. The double bond is the carboxylic acid, whereas the single O was the alcohol. So when we break it down, there's the alcohols again, and here's the carboxylic acid. Notice you added a hydrogen here and an OH group here. We added water to every single one of these to break it down into the alcohol and the carboxylic acid. Saponification is the final chemical reaction we're going to discuss with fatty acids. You're reacting a fatty acid with a strong base, meaning NaOH or possibly KOH. And you're ending up with a salt. Remember, a salt is all that is an ionic compound. Which means that you're going to have a positive and a negative interaction. It splits the glycerol, triacylglycerols, into glycerol and salts of the fatty acids. So it's very similar to this one where we're splitting it in half. But instead, you're still going to have the alcohol on this side, but this side over here is going to change. That OH is going to be a salt instead. And they form soaps. And we'll discuss why they're called soaps in a minute. Alright, so draw a line between the O's. Remember, this came from the alcohol, so we're going to still have the alcohols here. It's this part here that's going to be different than the hydrolysis. Instead of going OH there, we have O and A. That's why we have O and A over here. Notice the positive and the negative. That's what's making it a salt. Now, I said I was going to explain why they're called soaps. So that's what I'm going to do now. The oils on our skin are primarily nonpolar. This chain here is nonpolar because of the fact that it's all carbons and hydrogens. So this nonpolar chain here is going to interact with the oils on our skin. And then we have this ionic in here, which is polar, which is going to react with water. So once all the oil is mixed up with the nonpolar area, when you splash water on your face, this polar area down here is going to be pulled on by the water, and as it pulls on the carbon chain, it actually pulls the oil off with it. So that's why it's called a soap. Because it's taking because that's what soaps are made of. Because you have the nonpolar acting with the oil and being pulled off of the skin with the ionic end of it. Here's the 4 reactions that we've looked at total. Esterification is when we are actually making the triacylglycerol. So we're starting off with a carboxylic acid and an alcohol. Hydrogenation is when we're adding hydrogen to it. When we're referring to hydrogen, we're referring to H2. And you're breaking the double bond. Hydrolysis, remember the first part is hydro, which means we're adding water to it. Which means we're breaking it down into the original fatty acids and glycerols. So these two are opposites of one another. And then saponification is when you have a strong base. And you're going to end up making soap out of this. The glycerol is the same, but you're going to have O and some positive ionic compound. So if we were to write the product of this, we're adding hydrogen to the compound. So all these double bonds are going to break, and they're going to form single bonds. Because hydrogenation, you're going from double to single bonds. There you go. And that's the end of the reactivity of triacylglycerols.